All right. So the ability to transport Mars to orbit at scale, that's the first and biggest hurdle for the new space economy and for humanity to spread out across the stars, really. The second, scalable energy across space. Enter Ex Lumina. They're building Everlight, the world's first orbital laser power grid. This energy as a service utility aims to create infrastructure for a cargo ship type 1 and then perhaps a type 2 civilization by addressing the energy bottleneck of space. Kian Konrad Tajbaksh, the founder and CEO of Ex Lumina, is with me today. I also have Scott Walter joining me. Scott is a mechanical and aerospace engineer and two-time founder of robotics companies. Gentlemen, welcome. Great to have you with me on Over the Horizon.
It's great to be here, Royden. This is going to be an interesting chat.
Absolutely. Can't wait to get started on all things Ex Lumina. So, first things first, just for the benefit of my audience, Kian, let's just lay the ground and differentiate your company. Ex Lumina is focusing on the problem of space-to-space delivery of energy, right? And not space to Earth. Is that correct?
That's correct. Most people focus on like space to ground, but this is actually the technically more difficult thing. Also with the business side of things, so we focus mostly on space to space.
Okay. What's your competition like?
We have like two private companies and one government entity that works on that. Right now it's like we have like a little bit of a head start in front of them technology-wise, but they're catching up, so we have a lot of pressure to outperform them again.
Wonderful. All right. So how old were you? Were you 19 or 18 or a lot younger when you started this?
I started this company the day after my 18th birthday, actually. I was wanting to found it earlier, but I needed to wait until I turned 18 years old, like the legal age of starting a company, to actually start it. So it's now around 2 years we're working on that.
Okay, cool. That's great. Can I tell you a little bit of story?
Yes, please.
This was probably when I was like 10 or 11, and we used to in the summertime. I always go to my uncle's cottage for like pancake breakfast on Sundays. And the reason I like going there is my uncle always got the Sunday Boston Globe, which had a great section of comic strips in there and stuff like that. And every now and then there was like this comic strip that would be talking about, what tomorrow is going to be like with the future. And I'll never forget going in there, and suddenly there was one showing space-based power system. The whole idea of capturing it in space and beaming it down. I was like, wow, this is an incredible idea. And this is like a year before the Apollo landing. So it's kind of dating me a little bit. And I've always been excited by it. And then, of course, as time went on, the biggest problem was like, well, you can capture energy up there. We're just not sure how to get it on down. And you're going to microwave all these birds. And it's like, there's every single reason why it's not going to work. Yeah. So when I saw your application, I was like, that's brilliant.
Yeah, I remember.
He's found a way of being able to do it. So I'm really, really excited. And what I've been waiting, which has been about almost 60 years now, someone's finally going to pull the trick off. So congratulations.
Yeah, I got to tell you, Kian, I've rarely seen Scott that excited. Okay, he's
really yeah. I mean, when you go back to that 10-year-old kid and you're first learning about all these things and these Arthur C. Clarke ideas and von Braunian ideas, and then 50, 60 years later, you're disappointed. What happened to my future? My Buck Rogers backpack, So finally, yes, this is great. Tell us the details, because while it's not as technically challenged as going down to the ground, there's still a lot of challenges, and I definitely have lots of questions. But first, you lay it out. So I'm not asking questions that you're going to answer for us anyways.
No problem. I can tell you a little bit how the idea was started in the beginning. So we actually thought of doing Earth to like space to ground, and then quickly figured out that even though it's technically feasible, it wouldn't be economically viable. It would be unimaginably expensive because you lose so much of the energy you make by the atmosphere, like the atmospheric fractions and all the layers of air that are in between. So then we were brainstorming and thinking about why not use it on the moon. Artemis is coming up in a few years, and I need a lot of power. And right now the plan is to use RTGs, so radioisotope generators, nuclear reactors, which are insanely expensive and very difficult to build. So thinking about this might be a viable option. But then was the same thing, like how to get funding for that. Because it sounds like an amazing idea, but you need to somehow get actually the resources to build it. So brainstorming and then thinking about satellites in orbit already, like Starlink on this case CubeSats, because they need a lot of energy and they need to have like very expensive and big solar panels. Like this is like an image what we're trying to do. And usually every satellite, like the tiny CubeSats, have their own solar panels, and they're very constrained by the energy they can have. So the payload that's on board, like Earth observation or communication,
and it gets worse than that, because half their orbit, they are in shadow.
Eclipses, zones, right.
Which means they have to have batteries on board. So you may have a CubeSat which says, well, we'll only operate with, like, we're on the bright side and shut down. But the idea of the Starlink satellite is, like, at midnight, my Starlink is still working, which means it's got power on there. Where's the power coming from? It's coming from batteries. So it needs to have batteries that has enough power to last 45 minutes. And then on the other 45 minutes, the solar array needs to be big enough to not only keep it running, but to recharge it so it has enough on the end. So that's
right.
So you get the mass of the battery, and you have a bigger than you need solar array, because you need to collect enough power for both sides, not just one side.
And nearly half of the weight of a Starlink is just the power system, like the batteries and the solar panels. And you know how many Starlinks they're going to build. I plan to build 42,000 of these. Imagine how much batteries and solar you need to carry to provide energy for them. So Everlight is like the solution to that problem, because not only we can beam the energy from higher orbits that have continuous sun exposure, but we can also pool the energy between multiple satellites. I mean, in this case, this image shows 3 satellites being connected to one Hyperion. Hyperion are the satellites that actually create and send the energy. In this case, when a satellite, one of the customer satellites runs on idle, we don't need to send it like 100% of the power. We can just send it 5% or less of the power, and then redistributes the energy to a satellite that needs more power. So we need less total solar area to provide the same amount of satellites compared to if they had their own solar panels. So this is like one of the things how we engineer the market, product market fit to that, so we can actually make it commercially viable to do it.
Okay, so I definitely have some questions here, and the biggest problem is, of course, being able to beam energy from one place to another. So first, you're collecting energy that's being turned into electricity on the solar panels. You're using that to fire up a laser. So I'm not sure what the energy loss is there. And then the laser has to be directed over something that's able to receive the laser and convert it back to electricity. So what are the conversion rates on converting back? Is it, because it's solar panels are what, at best 20% or something like that with visible light? Are you able to do better?
Higher, much higher. So because
look at that smile on his face, that should tell you.
So
what is it, about
normal
40%?
solar panels, you're more even. So normal solar panels, you need to convert the whole wavelength spectrum you're getting on the panel, and you calculate usually with the atmosphere in between on normal solar panels. But for in-space solar panels, you can do some other things, because you can optimize them for specific wavelength. Like the receiver panel that gets the energy from our laser is optimized only on one single wavelength, and this is the wavelength of the laser. So we can get up to 68.2% around efficiency.
Okay, and is it basically a solar panel?
Yes.
It's the same technology. Okay.
It's the same technology. It's a little bit modified, so it can endure higher heat and stronger exposure from the laser, but it's basically a solar panel.
Okay, and you can make it a little bit smaller, I assume. So in theory, you could use existing solar panels, and it would work. And
we're going to do that for the first mission. Actually, we send it on an already in orbit. Right now, the satellite we're going to test on is already in orbit.
Okay, so but the problem with those things, they have to do all these different wavelengths and stuff like that. Now you can optimize it, which means in the future these things can be smaller. Now, how small could you make them in theory?
In theory, very small, but practically we're aiming to 10 by 10 centimeters. Because
that's small. Okay.
Yes,
now,
we're aiming. So
and how much power? How much power are you trying to put in that?
So for 1 square decimeter, a little bit around 30 watts.
Okay, that will be, because the big thing I'm afraid is that you're going to be way out there, and there's going to be some satellite there that thousands of miles away, and you're going to be beaming this thing, and hopefully it's a nice collinear beam, and you're going to hope some other satellite doesn't accidentally go past it and you don't fry it. I mean, because I'm just imagining like these superpower, but these are actually pretty weak, right? So if a bunch of satellites happen to cross the beam
through them, that's not an issue.
They won't even notice it. It's not an issue.
They're not, so in the beginning, we plan to make them much stronger, like multiple kilowatts of power, but there's no market demand because majority of the satellites are very small.
They
have like the power consumption of a smartphone. So having a few kilowatts laser is a little bit unpractical. But it's like nearly impossible that another satellite will go in between the line of sight of the 2 satellites that are connected, because space is so big. And in the case that it happens, nothing would happen to it.
But I mean, wait a minute. When's you gonna have those Starlinks up there? then it becomes a
If we
problem.
power like a whole Starlink burns more energy. Starlink burns like about, we don't know the exact measurements how much energy it consumes, but we estimate around the power of a Tesla Model 3 because it has Tesla batteries installed, so we're expecting it to have similar power consumption.
Right, and they want to up the power
to the Gen 3. That's going to be a lot more, right, Scott?
Oh yes, especially ones that will be launched with Starship. These will burn significantly more energy. So then we also have a much stronger laser for these kind of satellites. So then I would not recommend fly in between the laser.
And it seems like because the current generation is already bumped up the because they got approval to bump it up a little bit. So
they already increased it because they're doing direct to cell, like connecting directly to phones. So they need more power to actually reach the phones. So they increased already.
Well, my download speeds went up about 50%. Because of that, because the first thing they had to get FCC approval because there was something about how much energy they could beam down in a particular cell, and the problem is that they were doing different cells, and that you always have a little spillover from one cell to another, and all of them have to add up to be below some threshold. And I think they argued, wait a minute, we don't want to do that. Just allow us to get the maximum spectrum. So I think they were able to increase the download power by a significant amount, and as a result, everyone's speed has gone up quite a bit for free.
Is that also a function of the extra bandwidth? I think the FCC gave them some extra
well, that's for the direct to cell. So they get a new specific bandwidth for it. But in advance of that, they were allowed, I think, a month or two ago to increase the energy density coming down. And that has improved the speeds a lot. So yeah, we know they're going to want more and more power. And the problem is, if you want to have a lot of power going on, that means you need to have a lot of battery. It means you have to have really big solar panels. And it's just that vicious circle that makes it harder and harder. But now if you say, well, wait a minute, we can design as much power as we want, and we don't have to worry about the extra baggage that's going to slow us down.
Yeah. So eventually, is this going to be a constellation of your I mean, so how do I look at it? How does the average person watching my podcast kind of visualize this? It's a constellation, but it's made up of 3 essential technological blocks that are capturing energy, solar energy, transmitting it, and the third would be part of your client satellites, where it's converted from laser to electrical energy again.
Exactly. So it's 3 parts that make up the system. So the first part is the Hyperion. This is the one who captures the energy and sends it over the laser beam. These are like the super expensive big type of satellites and the most important ones, so where the most engineering goes into. Then we have the iris relays, which are basically gigantic mirrors with micro lens arrays, similar to like what Reflect Orbital is doing, but with space to ground. So we basically can reflect, or how do I phrase it, like readjust the laser beam where it needs to go for getting very far distances. And then the EOS receiver, which is like the micro solar cell that goes onto the satellite.
Okay. And that's so when you reflect it, there's very little loss on that. You're not doing a conversion, you're basically doing a redirect.
No, we're just reflecting. It's not like a flat mirror, so the mirror is a little bit curved, and we have a lens array, so we can basically refocus the laser beam again, because we have a big problem of divergence on very long distances. Like the laser beam spreads outwards over the distances, and we need to refocus them again so they don't get too big.
Okay, and how many can you redirect? Just one, or can you do multiple? Because if you're thinking of hitting thousands of them, I think there would have to be a lot of different relays.
Oh no, that's doable. We use we have a quite precise attitude control system, so we can angle the satellites where we need to, and we have no limitation how many can connect.
And I'm assuming it's not something like it has to react really quick. It's that you know the target, you know where it's coming from. It's maybe just a very slow procession to make sure that you're tracking it, right?
I mean, space, of course, these objects fly very, very fast, like 25 times the speed of sound, but because the distances are also as far away, it's barely a difference. It sounds like a lot, but it isn't that fast, actually. So
now you're not doing something like the spinning prisms and stuff like that sometimes used for laser redirects. You're actually talking about, you're going to just be taking a mirror and focusing it.
Yes.
Okay.
Similar like to the party lasers of having mirrors that turn.
Okay. Yeah, like that. Okay. Yeah. So it really is a mirror. It's not something else. Okay. And you can hit the spot that accurately. I mean, that's just amazing.
A little bit more sophisticated than just the mirrors, like silicon waveguides we're using for that. It's like the Pro Max version of a mirror. But yeah, it's precise enough for that purpose. Like we're still working getting it more precise. It's not like a finished thing. It's like we're iterating towards it. But yeah, it's feasible.
Now, when it comes to solar panels and space-based solar panels, I imagine there's a couple of things. There's probably like some really super efficient panels, but maybe they're either very expensive or they have like a lot of mass. So it's probably a trade-off to say, well, we would like to put these really good ones up there, but it's just too much of a penalty. In your case, you can probably put the best ones up there, right? That will be super efficient as far as capturing solar power. And then you have your conversion, and then you're only talking about maybe a little over 30% loss in the transmission, which is probably better than actually ground-based transmission systems as it is in many cases. That's actually remarkable.
But this is one of the good things you just mentioned with the quality of the solar panels, because the more efficient they get, the significantly more expensive they get. So most entities don't even use them. Like CubeSats have usually the cheapest type of solar panel that's available, but it's very heavily limits their mission uptime. So we can have like big satellites with big solar and hyper efficient solar panels and just beam the energy they need down to the satellite.
Now, is this designed to be sort of, literally you're plugged in constantly, or is it sort of intermittent that we'll beam you some packets of power and then you hold on to it and you just have a smaller battery that maybe gives you 10, 15 minutes of life?
A little bit like, so not really, you don't have batteries on board. It's a pulsed laser beam, so you have capacitors, but it's a very high frequency.
Okay, something like that. So okay.
Batteries.
Yeah. Okay. So if something happens that you don't transmit for a little bit, there's still enough onboard power to keep it going until the next transmission.
Beaming energy across space via lasers. This is crazy, because if I understand you correctly, your company is not only looking at Earth orbit, but also far beyond across space, Lagrange points, maybe the moon, Mars eventually, because if you're talking about lasers, and Scott, we've talked about this Starlink's plug-and-play system, which also uses lasers to transmit data right across, and we've discussed about how it could be used on Mars. You also now have the potential through Everlight for energy to be beamed across. Is there a convergence somewhere with what SpaceX is doing?
So SpaceX right now only does communication or planning to actually use energy, but we are actually planning to do it for the moon. So right now it's just like ideation stage, because there are not much public information from Artemis to how they're going to do the mission. But we already have plans how we can do that with putting satellites at launch points and beaming the energy on the moon.
Okay, the reason why there's not much public information about how they're going to do the mission is because they don't know how they're going to do the mission.
Yeah. I kind of fear that the Chinese will be on the moon before Artemis. Artemis has so many subsystems that are not existing yet. Should already be there. I mean, official announcement was 2024. It's now 1 year after that, and we're still not there. So,
Okay, so I believe one of your satellites is going up there on a SpaceX launch, or is it already up there in orbit?
No, not yet. So the first launch will be next year around, but it will be on a rideshare mission, where you do like a technical demonstrator, like test the technology over its limits, to find out where the limits are. And then the year following will be the first commercial satellites that will be launched. But they will be launched all on SpaceX for now. We already talked with Rocket Lab to use Neutron, but Neutron is not available yet, and it takes like a few years until they get commercially available. But yeah, the majority of launch vehicles that we have planned for to use is Falcon 9 and Rocket Lab Neutron.
All right. And how big can you scale up these? I mean, when you talk about satellite sizes, this is even, what is this, a Dove or a mini Dove size?
The first one is actually quite small. It's a little bit less than 1 cubic meter. I mean, it's very thin, because we put it into a dispenser and then dispense them like Starlinks in the Starship. And we have them as on top of each other, like on a cake, like multiple layers and satellites on top of each other. So they're quite wide, like they have a lot of surface area, but they're very, very low height. So they're very slim. But they're quite small, the first ones. The big ones, like the ones who we will use in a few years, they're much bigger, because we want to utilize the same dispenser like Starlink when Starship was available. So it makes sense to already engineer the satellites to be in the same form factor like a Starlink, so we can fit them on top of them.
Right. So next year, your first satellite is going up, probably a Falcon 9. What is what when you talk about systems generator, what is it going to have? Explain that for us. Is it going to be?
What do you mean?
Is it just going to be solar panels and a system to capture that energy, maybe capacitors on it, and then are you going to try and transmit via laser? Or what's how are you going to prove out your technology?
So the actual first mission will we will just launch the Hyperion with the laser on board and the tracking, and then we beam to already in orbit existing satellites. So we talked with a few space companies who actually have already satellites in orbit to test it on theirs. And then after this test run, we're going to launch the first EOS module into space. But we're going to start with the first Hyperion, because then we can already collect data based on just sending a normal solar panel. It's less efficient, of course, but it's enough to get the data and iterate on the design. Because the most difficult things are tracking and the divergence control, and we need to validate that this is working, and then we can launch the subsequent missions that have more sophisticated tech in it.
Yeah, explain why your choice of lasers and not microwave or any other form of transmitting energy. It might sound like a dumb question, but we've mostly heard about transmitting energy from space to Earth. So why your choice of laser, and how is it different? Because there's the whole question of how much you can control your beam, and that problem has come up when we look at laser energy weapons for defense. Is it the same in space? Explain this for my audience, please.
So good question with why we chose lasers to do. We experimented a lot. We researched a lot. We chose lasers mainly because of two reasons. The first thing is divergence control, like how far the laser spreads out. And the second thing is the efficiency from energy transmission, because microwaves are quite good to go from through the atmosphere, like from space to ground, and a laser would just not work at all. The upper air layers are already too thick for the lasers to go through. But because we're in a vacuum, we don't have this issue. So we don't need to use microwaves. The microwaves in general are very inefficient to use. They're only relatively efficient compared to a laser within the atmosphere, but in vacuum, lasers are the most efficient ones. Also, the laser's red, like on the image. We have a red laser for that. This is like the highest efficiency wavelength we can utilize for now. So this is why we chose laser over microwaves or radio waves. And the biggest problem actually in this entire tech, also with space to ground, is divergence actually, because tracking is not that big of an issue, because we already can track data lasers, like lasers that are for data transmission from Earth to Mars and even beyond. So this is not the issue. The bigger issue is how far the laser spreads out. So the laser we use fiber lasers, which have the lowest divergence you can get to, but radio waves would be very, very far out. So you would
So one of the common misconceptions.
So that's exactly the answer I was expecting, because I don't know how easy it is to really direct a radio beam, except maybe with phased array allows you to do a little bit, but still you get a lot of divergence. The other thing is I don't know how easy the energy conversion is, even if you can kind of keep it tight, how easy it is to take radio waves and convert it back to electricity. Whereas it seems that we know how to do, with solar panel type of technology, that you can take a light beam. So all those make sense. And because you're in a vacuum, and hey, why not? It's just the easiest way to do it.
Radio waves are quite a challenge, because also the receiver is so big, because the lasers, the phased array antenna spreads out so big. So that's why you see companies who market these space to ground systems have antennas that are bigger than the solar fields. If you would replace those solar cells, and even the receiver panel is bigger.
And even the phased array, I mean, everyone thinks, oh, I can take the beam and direct it in. It's no, it's got a lot of lobes. You get the central lobe where but you get all the others that is just spilling off all over the place.
Very far. Yes.
So you cannot focus it as easy as you can a laser. So there's winds there. And second, I think just converting it back into electricity is just way more efficient. The other thing I wonder is are they going to start designing satellites as somehow systems that actually run on light? On laser, so you don't even have to bother converting it back into electricity? I mean, that would be a rather interesting application.
So it's quite fascinating how much of the satellite's use case can be done photonically. Electronics means you use an electronic circuit board with electrons flying through, but there are also photonics, like photonic computers that use light to compute in general. We already brainstormed about that, if how much of the satellite we can make photonic instead of electronic. So this is quite an interesting. There's very few research done so far. There are a few companies who are working on it, like Light Matter, that works on photonic computing. So it's very early still, but I think in the future it might be quite a big deal because they have a lot of advantages compared to electronics.
Okay, would it? Is it lighter? I mean, it could be right. Maybe it doesn't
Lighter,
produce as
needs
much
less
heat.
energy and way less heat.
Way
So
less heat.
cooling in
Oh,
space is
tons
the
of it.
big issue.
Oh, okay.
Like the thing
This
is, there's no atmosphere to radiate through. Like fans don't
Mhm.
work in space. The water
Mhm.
cooling also doesn't work in space. So cooling in space is quite a big challenge, and photonics don't create any like very little heat. So
Well,
these solves most of
actually,
this.
water kind of does if you have it available, because it
If you have,
turns out
you need very big radiators to convert that into infrared and then radiates it out.
yeah,
outwards.
well, actually, you do see the Apollo astronauts. The way they were able to cool themselves is they actually did it from evaporative cooling, but that meant they had a consumable, so they actually had like some water that was evaporated that allowed them to do that.
But it doesn't work as
But it doesn't last very long. I mean, you get a couple hours and that's it.
You need basically to leak out the
Yes.
water.
So yeah,
how you get the water back then?
So like I say, you can do it. It's just not practical.
Yes.
All right, so I just want to go back to this image. You mentioned something about the red lines that we see. That's the laser. Now, is this near infrared? If I'm correct?
Yes.
Okay, so can you actually see it? Because I mean, it's kind of a dumb question, but everybody kind of when you see these videos of laser beams shooting across and taking down drones and missiles and all, people kind of, it's like, oh yeah, I saw that. No, but you can't see it.
You can't. No.
No, it's impossible because there's no molecules to reflect laser beam for. Like within the atmosphere, like in a foggy day, you see the laser very brightly, but then you go higher and higher where the air gets thinner and thinner, and you can't really see the laser, and then you're in a vacuum and there's nothing to react with. So you don't see any laser beam, unfortunately. It's always when I would look watch a sci-fi show and they have like lasers working in space, I always think like this is totally impossible. Like this is just...
Which is why you always see the guy like with these little cans or something like that to create the mist so you can see where the lasers are. And again, like the Ocean's 11 kind of stuff when they want to figure out where all those beams are, like you put something in there. So basically you're seeing the effect of the laser on the atmosphere. This is the same thing that when you see, whatever it says, the steam that's coming off of like the Falcon 9 when they're doing the propellant load, you're not seeing liquid oxygen or any of that. What you're seeing is it reacting with the atmosphere, cooling the atmosphere, and it's creating a cloud. So you are seeing fog. What you're seeing is water. You are not seeing liquid oxygen.
So your first satellite goes up next year. How do you see the scaling out? What are your biggest challenges to scale? Is it funding? Is it the technology? Is it a combination of both?
Mostly funding, because space is expensive.
Mm-hmm.
It always was, and it probably continues to be. It will always get cheaper, of course, because launching gets cheaper. I mean, launching was never as cheap as now. You can just go on the SpaceX website right here and then put in how much weight you have and just book it over the website, like you book a flight on Emirates Airlines or United or something like that. So, but it's still not cheap, like compared to like the normal living standard of a person. So funding will be the biggest bottleneck to scale. I mean, we're raising venture capital right now, but of course this takes time. So this is like the biggest bottleneck at the moment. We could guess that it will be probably for the next rounds too, because space in general, like the upfront capital you need is expensive. You need to have the launch, you need to have the satellite, you need to have operations, like all these things you need to have to actually start the system. It's not like a app you can vibe code within a day and then launch it on the App Store or something like that. It's quite a little bit more difficult to do that.
Yeah, and I suppose making that pitch will get a lot easier next year after you launch your first satellite and prove out your technology. Yeah, Scott, I get a distinct feeling we're going to be talking to this guy over and again over the next few years.
Now, I have to ask what I think everyone out in the audience right now is asking. First, you're 20 years old. Where did you go to school? Okay, where did you get this education? Because not every 20-year-old first knows this much.
18-year-old, by the way, 18.
Yeah, starting out as an 18. Yeah, you had to wait till you're 18. You obviously were formulating these ideas years before. You're well versed in the physics and everything that's going on, orbital mechanics. That I just find amazing. So, how did you get that background? And then I have a follow-up.
Mostly self-taught. So I always ask the question, because if you look at the total current media, everyone says AI.
Yeah.
And now I started this company when ChatGPT was already available. So I asked a lot of the typical dumb questions to the AI and did a lot of like try and error, like figuring stuff out, watching YouTube tutorials. But now asking myself, how did people start companies before that? how not people started companies before ChatGPT and YouTube and all of these things, like how difficult it was to get information, because right now I need to know something, I just ask the AI and I know the answer to. So it's a lot of trial and error you can do quite easy. Like the time between iterations is very, very tight. So it's I'm mostly self-taught. I mean, I have a co-founder. He has a degree, he has a master's degrees in aerospace engineering, but I started this company like a year before I met him. So, and most of that is actually like trial out, just try out to figure out, mess around, figure out these kind of things. So I didn't know in the beginning how it works. Most of the stuff I figured out on the way of trying to make it work.
Okay. Now the other obvious question is, you said you've spoken to to Rocket Lab, SpaceX, and others. I can't believe they actually took your call. You call them up, they started, and you say, by the way, I'm 20 years old. Click. They think it's a prank call or something like that. So how were you able to convince them that you're actually serious?
So this is a very fun story, because when I started out, I thought this might be my biggest challenge, that people won't take me serious, because I was like a teenager starting a space company. So try to be like in my position, thinking, okay, it's a teenager starting a space company. What can go wrong? But it's quite fascinating that this didn't happen at all. No one ever took me not seriously. This is the interesting thing. I talked with people and told them like my ideas, and everyone automatically, like, no one doubted the idea. And I in the beginning I would never thought about that, because when we look like movies or shows or like social media or these kind of things, everyone talks how difficult it is to start a company, how many people will doubt you or say bad things. It didn't happen at all. I think that there's a little bit of an overreaction on social media to that.
Sometimes, but it shows the power of an idea.
It's and the thing is, if people are fascinated by the idea, they're usually on your side. So if you talk to someone,
and you know what I bet every one of them did? I bet they did the same thing I did. As soon as I heard the idea, I was like, oh, of course.
Yes.
Why not even
everyone is automatically like flashed from the idea. So everyone wants to listen. As in one email to like Rocket Lab, they instantly answer. We have a call within the same week. So it's like you need to try to fascinate the people you're trying to reach out to, because they will reach out to you before you can reach out to them.
Yeah, it's a great idea and a great story. What's there not to back in this? So we wish you all the very best for this.
Absolutely. And where can we get that T-shirt?
Yeah,
we actually have a merchandise store. You can
you do. Okay.
Yeah. Website. It says merch up there. You can buy them.
All right. Great. All right.
Okay.
Next time I'll have it. Don't worry.
Let me just bring up your merch store so that we can do a little plug for you guys here. All right, there you go. I think you've got pretty neat stuff up there. I love your hoodies and your little badges. You guys should have a few stickers. I definitely get.
Scroll down.
Oh, okay, cool.
We have,
Oh, yeah, there you've got your badge sticker. Cool. This is really cool. All right, so let's go back to ChatGPT. Of all the AI models that you could use, why ChatGPT? I mean, Grok perhaps was not around, so I don't know if you switched to Grok or were you using Perplexity later on, or
interesting
Claude?
thing, because I was one of the first people who actually got access to ChatGPT before it got launched. Like I think nearly over a year when the private beta launched, I used already like the GPT-3 API. So I'm quite used to use OpenAI models. I'm still used to do it now, but a quite fascinating thing. Grok is better when it comes to orbital mechanics. I don't know. There's no information about it, but I believe Elon trained it with SpaceX informations, because it's too smart. It knows everything. You can ask it to create a slingshot like gravity assist to the moon. It will give you everything. And you try to ask the same thing ChatGPT, and it has no idea what you're trying to do. So Grok is very good.
I'm going to put you on the big screen now, and I want you to say that again. Come on, go for it.
I believe Grok was trained with SpaceX data, because it can do orbital mechanics. Very good. Like much better than like the normal person. Even if you have like someone who studies orbital mechanics, the Grok is better at it.
Okay, now the other thing is, like, it's very good, but the problem is how do you know it's good? Because most people, we would look at the answers from either one of them and we'd assume, oh, it's correct. But you know enough orbital mechanics yourself that you were able to validate it.
Yes. I mean, well, not only me, but also my co-founder, Vlad, because he's more sophisticated in orbital mechanics. But we both figured out that Grok is much smarter when it comes to that than every other AI.
Yeah, it's fascinating. Now, kind of going along the AI front is that everyone keeps on imagining space-based power systems and what they would be good for. And everyone's imagining, well, of course, what we're going to start doing is having server farms in space because we don't have enough energy down here. It makes way more sense to go ahead and put it up there. How would your system tie into? Because I think Eric Schmidt and others have already kind of proposed that idea. I think he may even have a company that's thinking of doing the exact same thing. And is there, I assume, since latency is not an issue, because I don't think it's necessarily being used for inference, it might be at a very high orbit, and therefore it will always be bathed in the sun and be able to do it and could have its own arrays. Or would this be something you would say, hey, we'll take care of the power problem for you. Just go ahead and put whatever you want out there for your server farms. Maybe there will be inference at low Earth orbit, in which case...
Makes sense to
do. Go ahead.
So the thing is, latency is not a problem. It's actually the biggest feature, because we right now calling over Starlink, and look how low the latency is. If you have like a server farm somewhere like in the desert where you have a lot of energy, or somewhere where you have cooling, like in Iceland or something like that, you need to send through underwater cables and have all the time the server banks who will, like the switches who will reconvert the signal again. So you have a lot of latency if you have like ground server stations. But if you have them in orbit and they can connect to another satellite fleet like Starlink, like Interlink communication, you have much lower latency. Like ChatGPT would have a much lower latency running in orbit than running on server farms, because right now, like I'm sitting in Germany, the OpenAI server farm is in the US, and it needs to go through the underwater cables till here. So we have a little bit of latency, of course, and having it directly above us would, of course, reduce this latency. It's actually the biggest feature of
and so,
and of course, then I mean, your underwater cables are also susceptible to sabotage or damage and all of that, So
yes, and they're quite slow because you have so many switches like server farms in between. You need to resend the signal again. Computers. So.
Yes, and now in space you would have compute, which you don't care about latency. You just, I've got to compute a lot of data, so I just want to have a large computer that has access to a tremendous amount of energy. And then you have the inference, which latency is a little bit of an issue because you'd like to work with it. So you see those two. So I could imagine people who are just trying to do compute might say, "Oh, we've got that solved. Just we'll put it on up there." But if you're going to start having the inference engines in low Earth orbit, then energy does become a problem. And that seems like a great solution. Absolutely great solution.
Yeah, it's quite useful that we can. So Everlight would be a big solution for these energy-hungry supercompute clusters in orbit, because we can send energy from orbits that have continuous solar exposure, so that don't need to carry batteries or go on idle at all. So you can get 100% of the power out of the compute cluster. Usually, you want to have like supercompute cluster at the lowest orbit as possible, and not because of latency, but because of radiation. You're in the Earth's magnetic fields, the protection of Earth's magnetic field. Further than this, you get more radiation, more and more, until your computer becomes useless. So radiation is a big issue.
But then you have the other problem is that you can't radiate the heat that you want to get rid of. Sometimes a higher orbit is a little bit better than being close to Earth, where you there's all sorts of problems.
Probably the supercompute clusters in orbit will have bigger radiators than solar cells, most probably, because heat is a big issue in orbit, in space in general.
I forget. You want to be below the Van Allen belt for all of that.
Yes.
Yeah, I mean, it just gets me thinking. There's been so much of talk about having all these data centers under the ocean because it's helpful to cool. I mean, Scott, I remember chatting with Brian Wong, who believes that the future data centers are all going to be on Mars, and you're going to have AI models that are going to be developed on Mars for Mars. If you have the energy source, you could literally deploy these data centers anywhere you want, right across. I don't know. We're talking level 1, level 2.
The other problem is cooling. Yeah, I mean, cooling is a problem, which is why you're either dropping them underneath the ocean or putting them up in Iceland. And the irony is that you have like a lot of energy that goes to run the computer, and then you get a lot of energy that tries to cool it down at the same time.
Yeah. So we were talking about, you've got Hyperion that collects solar energy. Iris routes the lasers across these orbits, and EOS converts beams to electricity on client satellites, right? Have I got that right?
Yes.
Okay.
Correct.
Are you planning to propose some sort of energy storage form, whether it's batteries or capacitors, something else, on your client satellites for redundancy?
No, because the the occasion that the system would fail is very low because we can just reconnect to another satellite. So if one Hyperion should fail out of some reason, it will just within milliseconds, much faster than the human the reaction of the human eye or something like that, it will reconnect to another Hyperion. The problem is solved. Only if the satellite, like the receiving satellite, gets damaged, then of course, but this is then not the problem of the network, and it's the problem of the receiver.
Right.
But usually, if one Hyperion should fail or disconnect, it will just reconnect to another one. So there's no need for that redundancy.
Now, are these satellites in
information.
LEO, MEO, or are they geostationary satellites? What's
Most of
first?
them will be in sun-synchronous orbit. So we have the high orbit of entire solar exposure, but the Iris relay stations will be in low Earth orbit.
Okay.
Yep.
All right. So you've got a layered system. And
Yes, the layered
where
system.
would let's say the first targets in terms of your clients, where would those satellites be, your client satellites?
Sun-synchronous orbit, because SpaceX transporter missions, the Rapture missions, mostly go into SSO. So the first customers all on SSO orbit. So we're going to start from there and then expand into LEO. Geostationary is too small of a market for now to provide that service there. Also because of the extreme distances to beam the energy towards there. Like divergence control, like I said, it's quite difficult on such a distance. But low Earth orbit and sun-synchronous orbit are the biggest markets we're gonna go to.
And what's stage one of your constellation that you would need to have up there in order to support a sufficient number of client satellites that makes financial sense for you?
So the first mission, or the first batch of satellites, will all go on the same transporter mission on SpaceX. So there will be all SSO. I cannot disclose the exact amount of satellites. We're also in iteration, so we try to get them even smaller than they are now, so we can stack more of them on top of each other. But like the critical threshold of how many satellites we would need, we need to test that yet. So we don't have exact measurements how much satellites we need to actually provide it, because we're still doing like iteration, design on the satellites.
So your first test satellite goes up next year. Is it in the first half or the second half of next year?
Around probably the second.
Okay. So let's say another year or so for you to get a sufficient number of your Hyperion satellites and up there.
Yes, around that. So 1 year after the proof of concept, like after the technical demonstrator, the commercial ones will follow, because we also need to evaluate the data, the results we got from the first mission. But then the building satellite is the easy part. Building the manufacturing line for the satellite is the challenge. Like the machine that makes the machine is the much bigger challenge than building a satellite. Because prototyping is easy. You just take a screwdriver, you put some parts together and try and error until it works. But trying to make 1,000 of them, this is like the much bigger challenge, because then you need to engineer like the whole production line, and this takes like around a year to do until it's get launched. And we also need to book the flight like 9 months in advance to actually launch it.
Right.
Okay. Now I get kind of another. I'm just trying to think of how this service works. Is that I assume most satellites, the energy requirements kind of come and go. It's not like it always needs 100 watts. Sometimes I need 70, sometimes I need 125. That means I would plug into your service and say, can you deliver me a continuous stream guaranteed at maybe 100 watts or 125, or can it vary really rapidly based on my requirements? Kind of going back to what Royden said with batteries, is you would probably have some sort of capacitance or something like that would store a little bit of energy. And then as you have variation, depending upon what your demand load is. And how do you do that? That means we somehow have to communicate back to your satellite. Are we going to do it through a laser link, or would that just be plain old radio waves?
So it depends on what are receiving antennas on the receiving satellite. Like if they use like S-band K-band or something like that, we would just send out their frequency. But there need to be constant communication for each other to actually send the energy from one to another. And we only send the energy the satellite actually needs. We don't send more or less. So the energy basically asks,
and you can
us,
switch like that.
5,000 watts, so we send 5,000 watts. And then it says, oh, we only need 30 watts, so we send 30 watts. We only need send the energy that the satellite provides, and then we also charge the customer only per kilowatt hour used. Not
how
like
do you moderate that? How do you do that?
Okay, so yeah, so that means you really the satellite is rapidly communicating to you. Say, I need this much, and what's the latency on that? So you're
it depends on the distance and which type of satellite, which communication frequency they're using, but like around 20 milliseconds.
Okay,
So
okay, it's
not
pretty
that
fast.
that
You might
much.
have just a little bit of buffering in there just to make sure you have
Yes,
adequate
I mean
energy.
computing and everything. So this is just like a rough estimation. It can be more or less.
Yeah.
It depends which type of antenna is used on it. We're also planning to expand that to computing and communication with the Hyperions.
Yeah,
So the first generation will just be power, because this is like the main core technology. But then we of course also put communication, like telecommunication, as well as compute on the Hyperions, so that you can basically outsource all of the complex work to our Hyperions if you have like a tiny CubeSat that needs a lot of compute and communication and power, so you don't need to carry everything with you.
Wow.
And then
Fascinating.
yeah, then the satellite, I guess, also has to have some form of kind of transponder. It's constantly telling you, here's where I am, here's where I plan on going.
We
Because
usually use the one that's
vary.
already installed. So most CubeSats have like S-band or K-band or like a radio wave antenna installed, and the latency of that is quite low. We also need very little bandwidth. We just basically send a text file saying how many watts we just need right now, and then we send energy. So that's not that. It's not really
but as far as like the location, you have to know where to track it, which means somehow it has to update it, especially if it decides it's going to change orbits, or I mean, there's always orbital decay. Everything else is going on there. They're never exactly where you think they are. And I don't know, I don't think satellites have transponders on them, do they?
They have. So it depends on the
they
height,
do.
which orbital height they have and which inclination. Because usually GPS also works in space if you have low enough of an orbit. If you're underneath the GPS satellites, because GPS satellites are usually in geostationary orbit, so you have a lot of space in between to Earth's orbit, where GPS still works, but you have very, how I say, not latency, but you deviate quite a lot from the GPS coordinates. So it's like more than 30 meters off where the actual satellite is, because also not only of the speed, but also the GPS satellites are not built to identify objects in space. You're basically forcing them to give you the data and then estimating how far it needs to be.
So
that means GPS too.
So all the satellites are basically pinging. They're out there. I'm here. And all the other satellites can listen in, or is that something for ground-based systems? Because I assume the spy satellites, they're not doing that. You know?
No,
they're not letting anyone know where they are.
So GPS usually works. The GPS satellites itself only send a signal, and you basically triangulate the position where you currently are by the latency of the signal arriving to you. So you actually need to send the coordinate. The receiving satellite needs to send the coordinates to us to figure out where it is. We cannot track it from ourselves.
Okay, so it's sending it directly. It's not like anyone can just be listening to where all the satellites are up there.
I mean, otherwise military satellites wouldn't work.
No, that's what's it's so like, aircraft have transponders, which basically means anyone could track aircraft anywhere that they want to be unless they turn it off.
But it's like a public protocol. It's not the technology.
Yeah. Okay. In this case, so the satellites are kind of quiet.
Yes, they're quiet. So they need to send. We need to be in communication with the satellite to send energy. So we need to have rough GPS coordinates, and the rest we're going to do with LiDAR sensors. We actually use the onboard laser for the LiDAR. So we measure the time that the light takes to go to the satellite and then bounce back until we receive it again. So
that's what I figured.
Like the position, but also the exact distance.
Yeah, you'd have a pilot beam of some sort to say, okay, that's where it is, and now run it down that.
Yeah, exactly.
And you could use that pilot beam probably also for communication, two-way communication.
Yes. Yeah. We use the same laser array for that. So it's just like the different software that tells it, okay, now we just send a little bit of energy to know where it is, then a little bit more for communication, then a lot more for energy.
You reposted this. This was from Ex Lumina. And I found this really interesting because it also demonstrates the back and forth and how responsive you are to your clients. So you said here, in recent talks with satellite operators, we discovered something unexpected. EO, that's Earth observation satellites with deployable solar panels, often suffer from jitter, which leads to shaky images. By powering them with Everlight, they can remove the deployables entirely, eliminate vibration, and deliver sharper and more stable imagery. Break this down for us. This is fascinating.
So that's actually fascinating because we would have never ever came up with it ourselves. It only happens because we talk to customers who actually operate Earth observation satellites, and they came up with the idea and asked us, does it remove the jitter? And then we of course did some research after the meeting and then figured out, yes, it does. And then we figured out that we are
here's a solution we didn't
same
think
issue
we
with
could provide
jitter on our satellites. So that's why if you pull up the image of the commercial satellite, like those images I sent you, you see it looks very unusual for satellite compared to like a normal satellite. I mean, if you show the image, because we have you don't see it on this specific image. I don't think I sent it to you, but we have a Z-axis gimbal here. We have a Z-axis gimbal connecting the solar panels to the frame of the satellite to remove the jitter. So basically, like a DJI gimbal on a drone, we basically actively do like noise canceling. We send a like a resonance signal through the electric motor in the gimbal to compensate for the jitter we create on our own satellite. But because the technology is so sophisticated, it doesn't physically fit in such a tiny satellite. You cannot put a Z-axis gimbal in a CubeSat. It doesn't fit from the size. So Everlight solves this issue by we have the Z-axis, like the jitter compensation. We just send the energy with the laser beam to you, because we don't see particles, but only like light. We don't have any vibrations. So we don't have any jitter, and we have very clear images on Earth observation satellites.
Okay, so the jitter is basically there's vibrations going into the main part of the satellite as a result of this huge
because you have
wing
reaction wheels, like the attitude
Yep.
control system has reaction wheels that where it basically shows like the angle the satellite's angled at. And these create a little bit vibrations, and that usually not an issue. But the solar panels reinforce, like the amplify the signal, the vibrations. Like a guitar, you play on the guitar, and you have this hole in the middle with the resonance body around it, and this amplifies the noise of the guitar. And you have the same issue with the solar panels. It amplifies the vibrations that the reaction wheels create in other systems that move around, like cooling or these kind of things. And this is quite a big issue, actually. Also, mostly for Earth observation satellites, also for communication, because the laser will jitter out, so it will vibrate back and forth. And a little bit of a vibration on these extreme distances is like you're totally off course. So this is like a thing we only figured out by asking the companies.
And that makes sense, because a big wing like that, which is what that is, you have a little bit of vibration. And it's just very difficult to damp out. It takes a long time.
Yes, but this only happened because we're developing the system with the feedback of the customer. It's not like we're assuming and then build it on it. But I always say, instead of assume, just ask, because even asking dumb questions, at least get some answers. And in this case, it was a very good answer.
Hey, you're preaching to the choir here.
Yeah. No, that jitters. It's interesting. I imagine there could be all sorts of sources for. One, you say like the reaction wheels, but depending on where they are, there's a little bit of drag on those things. There's constantly something impinging on those.
And also, and also another thing is on satellites that fly in very low orbits, you still have some atmosphere there, like some air molecules, like the ISS. And big deployables slow you down a little bit and then reduce the mission uptime of your satellite. So we also remove that because we don't need any deployables. So basically the cross section of the satellite is so small, it's very aerodynamic to say. That you don't need to account for it to fall down, basically.
Okay, now, all right. So here's the pushback that you're going to actually get from some people is that all the satellites need to be able to deorbit somehow. And one of the safety features of Starlink, if for some reason they actually run out of propellant or something happens there, because you have the reaction control wheels on there, you can kind of set up the attitude of your solar panels to try to do something to bring you down. It's not the ideal solution, but it's kind of like a redundancy. So as anyone comes and goes, wait a minute, what's going to happen at end of life to make sure that we're able to bring these things back out of orbit?
There's actually a thing that needs to be accounted for. It even says it in the SpaceX user guide that we need to account for how we get rid of the satellite after its mission is over.
Yeah.
So, of course, our satellites also have deorbiting systems installed. So after the mission lifetime, we can deorbit them.
I think the simple thing is you just have like this big balloon that just and suddenly, oh, look at this, all this surface area. And then that's just going to eventually cause you to deorbit no matter what. So that's the other way. But most part, you don't want to have that big wing out there for no reason.
Yes. Because, I mean, most satellites don't have a propulsion system. So they don't have the ability to just increase their orbit again, like the ISS or like the Starlink has ion propulsion systems. Our Hyperions have it too, but most satellites don't have them. So they're just dead afterwards. Because propulsion systems are not only expensive, but also regulatory pain in the butt to get certified. So because not only you need to have the propulsion system in general in it, but you also need to have pressurized tanks. And then you need to go to the payload user guide of SpaceX, and you need to certify them, and it takes months or years to get that actually approved. And then so having the ability to get rid of propulsion for the customer satellites and just reduce like the drag it creates is quite convenient for them.
Yeah. So I was going to ask you a follow-up question about SAR, but since you brought up propulsion, I think that's a brilliant segue to talk about propulsion enhancements that Hyperion offers, right? And Ex Lumina offers, because it's like it's not just. What do we mean by propulsion in space? What are the uses? Orbital maintenance, perhaps even deorbiting emergency maneuvers in space. And so, what are we looking at right now? Mostly chemical um, thrusters, gas thrusters. But then you also have ion thrusters, which work very differently, and they're a lot more slower, perhaps less effective. You can't use them for emergency. Is there a use case here with your solution?
It's quite interesting. So I don't know if you heard of the company Pulsar Fusion. They develop mostly ion thrusters, but work on thermonuclear thrusters using nuclear fusion. And they had a big issue that the engines burn like a lot of energy, like over 10 kilowatts for like a tiny engine. So they were not actually feasible to put them on any satellite because they burn more energy than most satellites can create at all. But the cool thing about Everlight, you can put these engines onto your spacecraft and just send the energy over the laser beam. You don't need to have all the weight of your own solar panels, because the solar panels that send the energy are stationary in orbit, like our Hyperions. They don't need to run on propulsion systems, only if they want to deorbit or change like the inclination or something. But you can just send the energy through the laser beam to the spacecraft that's actually moving to reduce the mass, and then put full power onto the ion thrusters or in the future nuclear thrusters to get where you want to be. So we talked actually with Pulsar Fusion about that concept. And that's actually the engine we have shown here on this image. This ion engine is actually Leo Bear from Pulsar Fusion. We're going to use the engine on our own satellites too. But the cool thing is, with the really big engines like 10 kilowatts and above, we can just use multiple laser beams, like multiple Hyperions, send the energy over to the spacecraft that's moving, and get to Moon and Mars very quickly. That's quite interesting.
Wow.
Yeah, it's definitely, that's what makes ion propulsion is interesting. It's not your normal chemical base. So to go anywhere in space, you need energy and you need propellant. You need something to throw out the back end to get the reaction force, and then you also need the energy to do it. And chemical rockets do that in all together in one, because the fuel source is also the propellant. That works nice. The ion engines, they're a little bit nicer, not as high thrust, but you still need an energy source. So you don't. So where are you getting it? Well, you're getting it from the sun, which means, as Kian just pointed out, you need this big solar panel, which means you have to carry the load of that along with you. And if you can dispense of that, man, that gets a lot better, because remember, the tyranny of the
so
rocket
much faster. Because with the 10 kilowatt example, like the amount of solar area you need to get 10 kilowatts, and this is incredibly heavy. But getting rid of all of this unnecessary tech, you just send energy towards, and you can fly to Moon and Mars very quickly.
And a lot of problems with the ion engines is not the amount of propellant you've got with you, but the amount of energy that you have available, which will be limited by the solar panels. But now you can ramp that up. You can get a lot more acceleration out of it, which will be cool. Now, the other thing, potentially, could you should be able to use this for solar sails.
Yes, we actually calculated. So there was a project called Project Starshot. You heard of that, where they wanted to use microscopic, like really, really tiny spacecrafts, and then send them to Proxima Centauri B, like the closest star system we have. And theoretically, that concept would work. Practically, it doesn't. We calculated multiple times if you can use our own Hyperions for that. And the biggest problem is actually the divergence. As soon as you're beyond the moon, the moon is still quite far away compared to like Earth's orbit, but even that is technically feasible to beam energy to the moon. But everything beyond that is nearly impossible, because the divergence is so big that the energy that's received on the other side is so little that it barely has any impact, especially with solar sails, because solar sails only use the impact that the photons create on the sail itself and then reflecting back off, and this little bit of an impact on this large like years of acceleration, like gravity assist, gets you moving forward. But because of the extreme distances, the light that comes there is insignificant, so it doesn't really work, especially for interstellar missions, at least not for now with current laser technology. We were thinking about if this would actually be feasible. We even reached out to multiple companies to figure out how the subsystems work, like making the satellites on tiny silicon wafers, on silicon dies, and as small as possible. But the divergence is actually the biggest problem. You can make
Hey,
like
have
a gravity assist.
you thought about Perskovite cell technology for solar panels?
What do you mean? How it's called?
Perskovite.
Yeah, Periscope. I think it's one of those that gives you a couple more percentage. And there's probably so many things you could do with those panels, as far as whatever cooling you have to do to make sure you boost the efficiency.
So the biggest thing is also the costs usually.
But I think Perskovite, the idea of that is it's trying to capture as many of the wavelengths as possible, because a lot of the problems is a lot of the energy that comes through you lose. In your case, you don't have to worry about it because you're focusing on the ideal wavelength, so it may not be necessary. Cooling is like the only thing is that solar panels like to be cool. They don't like to be hot. But Kian, I think you can probably help either brainstorm or answer some questions we've had, because we've always
Sure.
talked about being able to do communication between Mars and Earth, and how Starlink satellites will play a role in there, and using like the plug-in lasers and everything else. And so I sort of managed like, well, you really can't beam your data rates over that long distance are really bad when you're using radio waves. So if you're using laser, it's going to be a lot better, but you're still going to have divergence. And the assumption is there's no way you can beam it straight from Earth to Mars, and then depending upon, when you're in opposition and stuff like that, it doesn't work. You're going to need some sort of relays. I imagine, well, we're going to have relays and Lagrange points, a bunch of those around there, and they will just become relay stations that will probably use lasers. Now, are the Lagrange points close enough to be able to do that networking bouncing around, or are they still kind of out of range, and would you have to put something else in there to account for the divergence?
So divergence for communication isn't even that big of an issue. You just set more energy to compensate for it, because the energy requirement for data is so extremely little that you only need to receive like fractions of like milliwatts of power to actually receive the signal you want to send. So having like divergence that goes to hundreds of kilometers, a distance is like a width of the laser beam that arrives there, is not the issue. The only thing is if you need to shoot it through an atmosphere, then you have problems. So usually you want to have and interferences are also a problem. So usually you want to have your satellite somewhere in a close Earth orbit, so you have direct communication with Earth and space, and then the other one around stable orbit around Mars. To send energy. You don't need any relay stations in between, because the energy that needs to be received is so little that you can send as like, even if you only send like 30, 50, 40 watts, even if only milliwatts or less than that arrive on Earth, still get the data you want to.
So I'm only so maybe you only need the Lagrange points that allow you. They could be Earth Lagrange or Sun Lagrange points, just to make sure you can go when you're in opposition.
Oh no, the sun is on all these renderings. The sun is so big, but in reality the sun is so small you can send directly through it. You don't need to curve it around the sun. The sun is very, very tiny in this gigantic scale of our solar system.
On the giant, but I'm still thinking there's like, isn't there right now? There's what?
This is less than a millisecond where you have perfect on the other side of the sun.
But I thought it was like some of the communication with Mars, at least with the radio waves. There's like a couple of weeks.
Oh no, radio waves have a lot of interferences.
No, okay, so with the,
I mean, like the light. Laser beam,
okay,
like
with
infrared or UV light, like this.
So you don't have to like hit one and then get around to the backside. So you're not doing a pull bank shot at that point.
No. This has always fascinated me. This question, isn't the sun in the way? On all these renderings and all these movies and shows, the sun is so gigantic, big
it's kind of small.
The solar system. But if you look in reality, it is not even 1 pixel. If you look like on a 12K screen, it's not even 1 pixel. The sun. So big is the width of our solar system. So you can just send directly through it. You will not reach the sun anytime soon. It will be millions of kilometers in between.
So in theory, there's going to be like a short period of time and it doesn't work.
It's less than a millisecond where this could happen.
Wow,
this is like very little time.
That's small. Oh wow,
so the
super rare event.
So insanely fast, and the sun is so tiny compared to the speed of the entire solar system moving, that this is not an issue at all. Like this concept of needing to bend the signal around is not really a problem. Only if you have a signal that is subjected to a lot of interferences, because the sun creates so much radiation that you interfere with the same signal. But if you use like everything between infrared and UV light, you can just send the signal directly in the world. As soon as there's not an object in between, like dust or like air molecules or something, that's not an issue.
Okay, so there's absolutely no need for relay stations.
No, not for communication, only for energy, because if you have large divergence, the energy that's received is too little to actually be utilized. But for communication, the receiving end has such extremely precise antennas to receive the signal that can always get the signal out, and you have insane bandwidth, but just the latency is whack. You can transport terabits a second, not an issue, but then you have like between 7 and 45 minutes latency.
See, I always learn something new on Over the Horizon. Yep.
So you've touched upon fundraising, but just give us a high-level, zoomed-out view of the timeline that you're looking at. So next year is the launch. The year following will be commercial implementation, but between that there are a lot of milestones they need to make it work. So one of the upcoming test runs is testing the laser beam from a UAV, like testing it on a drone.
like beaming energy from drone to ground and then drone to drone, because this is enough of a technical demonstrator to also show investors that the tracking works, because it's still a very difficult system to make to work, even though it can be explained very easily. It's much more sophisticated than it sounds. And this is one of the test runs we're going to do on UAVs. Then, of course, the vacuum testing, on radiation testing, because radiation is also a big issue, especially for the sensor who is tracking the other satellite. Also for the compute. I mean, we are in the Van Allen belt, so we have not that big of an issue with radiation, and if we would be like on Moon or Mars. But that's like one of the things we're gonna test. And then the Orbital test run. We were gonna launch on a Redshift mission. So also on a Redshift satellite. So it's not only our satellite, it's like one of the subsystems we're gonna include. It's mostly because it's cheaper and faster. And then we're gonna launch the first like fully our own Hyperion satellite. We're gonna test also all the subsystems and everything else. So this is like the timeline. So it's around 2 years until we figure out how the system works on scale.
Wow. So so you think you'll have this up and running before your 25th birthday?
Yes, for sure, 100%. So the timelines in space are actually not as big as it sounds. So usually we need to book 9 months in advance for rocket to actually launch. But this is like the optimal, like I'd always say, the economy class booking. But you can get it in 6 months, and if you put a lot of pressure on them, you can get it into 3 months. But right now we need to book 9 months in advance. But if we would be under pressure, we could get it to 6 months maybe down. So we can do a whole mission from ideation till in orbit in less than a year, realistically. We could do it in half a year, but this would be like a lot of headaches and sleepless nights. But like realistically, well, like with enough buffer time, it's around 1 year that takes from ideation till the satellite is built, like tested and certified, and actually in orbit and everything else.
That's still remarkably fast.
Yeah, it always like perceived to be like 5 or 10 years, because the big like government missions take like decades. Like James Webb Telescope took like forever from ideation to launch. And all the other government satellites too. But private satellites are much faster, especially because of SpaceX has a very high speed of iterations. Like they're measuring things in days, not in months or years. So it's very easy to plan new projects with them because they're always available. Like we can call them at any time. So it's not like in Germany where everyone is not working on the weekend, and then this person's on vacation and this person's on vacation. SpaceX has a very, very efficient
I know all about that.
Company. I mean, it's the most valuable privately held company in the world. And you would assume that because it's such a big construct of governance, so many people, it would be very slow, but total opposite. I like totally. For such a big company, it's insane how fast they can move forward.
Okay, so I have to ask you this and play the devil's advocate and ask you, what is your moat? What is it that you and your team bring to market in this solution that others cannot replicate, or someone with the big bucks cannot come in and do this much quicker?
So I got this questions quite a lot actually, and I always used to give a different answer. But now I would say it actually would be speed, like the speed of execution, because technology-wise, everyone can copy that. Like it's not that of a USP technology to do it. Like if SpaceX wants it, they can build it themselves. But it's mostly the speed of how much progress we're making in the last few months, or like since the project started, that I would consider our mode. Because we have some private companies who work on the same tech, like Starcatcher or Pulse Space, and it took like 2-3 years and barely any progress they made. At least they didn't announce any big test runs, anything. And within a few weeks, we got from one test run to another, and then this and another contract in here. So a very high like cadence of innovation that's happening right now. So I would say our mode right now is like the speed of execution.
Yeah, I think exactly that the advantage is that you don't have lethargy. All the other companies, they could do it technically, they have it, but they just move so slowly. And they just think in
especially
decades.
The bigger the company, the slower they move, except SpaceX, of course.
But
usually they have, we talk with a lot of government entities doing like since the start of the project to now, like from the DoD to a lot of government run companies, and they move so insanely slow. Like a meeting that took multiple weeks just to get one meeting, and then the next one took like 2 months, and that's like alone just the time they take to reply to an email. imagine internally how long it's gonna take to just start building prototype. It's like 3 to 6 months happening and barely any progress. And we usually take less than a week from ideation till we have a new iteration of a prototype. Like with testing, everything included, like takes around like 4 days right now to build like an entire prototype of a satellite and test it, and then destroy it again, because we usually want to test it above like the limitations they can handle. Instead of like assuming how much it can handle, we just put as much power until the laser burns out, and then we know, okay, this is like the peak power it can endure. Let's do the next run of more power. Like I would say it's the speed. Speed is our mode right now, because technology-wise, if SpaceX wants to have it, they can build it, but they're too focused on Starlink right now, because this is like the baby, basically the most important thing for them right now. And also, every like big company who has the resources to do it will take like years until they have a prototype.
Thank you so much, Kian. It's been wonderful talking to you. Thank you, Scott, for joining us. And I suspect we're going to be talking with this young man a lot more as his project progresses. And let us know when you're fundraising. Nudge, nudge, wink.
Oh, you would say, I will post for sure on LinkedIn. Like, there's a lot of things happen lately. Will come way more in the future.
All right.
Okay.
Thank you so much.
Thank you, Kian.
Appreciate being invited.